Hi everyone, thanks for coming. My name is Jeff Zemerick. My co-presenter, Suneel Marthi, could not be here today due to a last minute work thing, you know how that goes. So I'm on my own today. But thanks for coming to our presentation titled Embracing Diversity, Searching Over Multiple Languages. So our agenda, we're going to ask the question, what is multilingual search? Why multilingual search? Why do we need it? What is neural machine translation? And last, we're going to look at a multilingual search pipeline. In the keynote this morning, they talked about how these types of technologies have really reached the point where anybody can use them and make use of them for real-world applications. And that really hit home for me a little bit because I feel like I am the embodiment of that person. I admit that the tools that we mentioned and we talk about in the pipeline, I'm not an expert on any of them. And we could probably have a week's conference on every individual single tool in there. But I think it really goes to show that someone who wants to use these tools can and get good results for a real use case. So first, what is multilingual search? Pretty much what it sounds like. You're searching over content written in different languages with users speaking different languages or both. So anytime that we have text that's in different languages than our native text or someone else's text, and we need to manipulate it and we want to search it and get information out of it, that's multilingual search. Multilingual search involves parallel corpora, translating queries between languages, and then, of course, translating documents into the language that you want it to be in. So that was easy. What is it? Pretty self-explanatory. Now, a bigger question. Why? Embracing diversity, the title of our presentation. I grew up in the coal fields of southern West Virginia, and other than when we went on a family vacation or when I went to college, I never heard anyone speak a language other than English. And outside of southern West Virginia, that's not how the real world is. There's many languages. Get off at the airport here in Montreal, and you're more French than English at times. So we have to embrace diversity out there to be inclusive for everyone. And if we want to put some numbers to it rather than just anecdotes, if we take a look at the dumps from Wikipedia for various languages, we can see that there's about 62 gig in English, followed by about 17 for German and 10 for Italian. So we're definitely English heavy, but there's still 27 gig in just this of non-English content that we might be missing out on, or that German or Italian speakers want to take advantage of. And a good number of non-English speakers, and instead of a good number, a better phrase there would be a lot. There's a lot of non-English speakers in the world today. A lot of queries are composed in English, and that's due to kind of the text. A lot of technical text sometimes is written in English. Research papers is kind of English heavy. So a lot of queries are still composed in English. And a lot of times it's preferable. You want to return search queries in your native language so that you can make sense of them. If being an English speaker and I don't speak any other languages, getting a document back in French, it probably won't be a lot of use to me. You want to get that document back in your native language. An example use case, tech domain. A lot of it's English language. Another one, native only. And this screenshot here of a web page kind of describes the system that I'm going to describe later for an English in, English out search. I'll talk about that a little bit later on, but sometimes you want to search over multilingual text and you want to give it an English query and get English results back. So now, what is neural machine translation? The keynote this morning, again, a great introduction. I kind of felt like my job was kind of a little bit done. I had some help there talking about neural machine translation. At the simplest, neural machine translation is just deep neural networks applied to machine translation, translating text from one language to another. Like the translation technologies before it, you have to train on bilingual corpora. So you need text in one language and the text in another language to train on. And as we heard this morning, pretty much any type of training, the more data you have, the better. So when you can get all that data, you'll get better results. And also we heard this morning, translation happens per a probability distribution, one word at a time. It was mentioned that as the algorithm progresses, it determines what word is next, one word at a time. And also attention this morning was mentioned, which I thought was phenomenal, about how when attention was added to neural machine translation, that the results greatly improved. And that paper down there is a great resource for getting into the nitty-gritty details about that. So before neural machine translation, we had statistical machine translation, SMT. It, like NMT, trains on bilingual corpora. Think about the early days of Google Translate. It was statistical machine translation and all the other online translator websites. The blue in the bar chart is the statistical machine translation scores when determined how did the translation do. The orange, it starts in about 2015, is neural machine translation. And you can see then that in 2015, neural machine translation was a little bit behind. And then 2016, it passed statistical. 2017, the blue line's gone. It's just kind of like, okay, you know, let's move on to what's next. And it was at this time, 2016 or so, that Google dropped their statistical machine translation in favor of neural machine translation. So I think pretty much all the big services today rely on neural machine translation. Just a little overview to kind of let you see the differences a little bit. This table glosses over a lot of stuff, but it's intended just to give you a very high-level overview of some of the differences between neural machine translation and its previous generation statistical machine translation, just so you know what we're comparing, what we're talking about. An example of an NMT toolkit is Sakai, that I'll talk about a little bit later on. And the equivalent for statistical machine translation was Apache Joshua. Maybe some of you have used these tools and are familiar with them. NMT, high-quality translations. Statistical, reasonable quality, as we saw in that last chart. Sakai is written in Python 3 with C++, and Joshua was mainly Java with some C++. Neural machine translations knock it out of the park in terms of model size. A Sakai model, 300 meg. Apache Joshua model, 60 to 120 gig. If you remember the days when you started downloading, you go to bed and you hope it finishes the next morning, that's kind of, you know, that's where you're getting at there with those giant models. Neural machine translation, simple training process, was talked about this morning in the keynote as well, and the translation cost between the two. Some samples of neural machine translation. Like I said, I am only an English speaker. If anyone can speak, I think, German, you probably get more insight out of this slide than myself personally can. But based on the green text from the translation, it makes sense to us. So it seems to be a pretty high-quality translation. And a second example, you have a little time but want to burn fat and build muscles. Again, that makes sense to me as an English speaker. So definitely high-quality translations coming from the NMT model. Anytime we have translations and we have our bilingual corpora, we always have a problem of what do we do when we see words that we haven't seen before. Your bilingual corpora can only have so many words in it. You're always going to run into a new word, some new text-speak thing will come out or something. There's always going to be something new. One way to deal with that in a paper published 2016 was the concept of using byte pair encoding. And byte pair encoding is not a new algorithm. It's been around since the early 90s as a simple text compression algorithm. But in this paper, it was adapted to be used for handling unknown words. So byte pair encoding, it makes the NMT model capable of open vocabulary translation by encoding the rare and unknown words as sequences of subword units. So instead of looking at a whole word that may be unknown that we haven't seen before, we can now focus on 3, 4 letters in that word that we have seen before to help us with our translation. For an example, a phrase which doesn't make a lot of sense, positional addition contextual. If we apply byte pair encoding to this phrase, we can replace all of the TIs with X's. Going further, we can replace AL with Ys. Going further, we can now replace XOs with Zs. So you can see where the groups of letters start appearing as you go down through the algorithm. And so at the end, you can, the neural machine translation can use these to help figure out what are unknown words based on where it's seen these patterns before. So with byte pair encoding, we open ourselves up to be able to use an open vocabulary. To prepare for this presentation, I trained the Sakai model for English to German with and without byte pair encoding. And it's pretty remarkable, the difference. Without using byte pair encoding, you get a lot of unknowns. The algorithm just doesn't know what to do. When you train it, again, using byte pair encoding, you get no unknowns. Maybe that was my case. Maybe we'll get some later, but it filled in the words reasonably well. And this is the code on GitHub for the subword MMT. It's written in Python. You can use it with Sakai. The paper and the code are really good references. And if you're interested in this, I highly encourage you to check it out. And all of the links that are referenced in here as well. So for the last part, I want to look at a multilingual search pipeline. So what we're going to do is we're going to take Solr, we're going to take Sakai that we saw, and we're going to take some other tools. And we're going to put together a pipeline that does English in, English out searches over multilingual documents. So what I did is I took news articles that are English and German, and I indexed them into Solr. And I want to search over those articles using an English word, and I want to get the responses back, the results back, also in English and summarized. So that's what our pipeline will do. So the pipeline tools that we'll use, Apache Napa, Apache Open NLP, Apache Solr, Sakai, and recent work that just came out, Get to the Point, Summarization with Pointer Generative Networks. I couldn't come up with a real good name for it, so that's the name of the paper. It's another one that I totally encourage you to check out if you're interested. The code is up on GitHub, and that's the code I use for this presentation. Everything here is, of course, open source, so you can use it to your heart's content. Apache Napa, briefly going over these tools. Dataflow Orchestration. So it allows you to take data from one place to another while doing stuff to that data. It's great for any time that you want to move data through some kind of pipeline. It gives you a visual interface to drag and drop the steps in your pipeline called processors. You can link them together, do things with them. I'll show you a little bit the pipeline I set up for this. Out of the box, it comes with a Query Solr processor, which is fantastic. All I had to do was drop it onto my Napa canvas and my flow, configure my Solr endpoint, give it some search terms. It did the rest for me. So it's really baked in from the start, makes life nice and easy. Apache Open NLP. I failed to mention at the beginning that myself and Suneel, my co-presenter who could not be here, we are PMC members on Apache Open NLP. Our pipeline uses language detection, sentence extraction, and tokenization. We use language detection, of course, to determine what language our search results are in so we know what to do with it. Sentence extraction and tokenization are used to pre-process the text before it gets summarized. Those are just two necessary steps that the summarizer requires for it to do its work. Apache Solr, I won't put a lot up here. Just a summary that I index about 100,000 English news articles and about 30,000 German articles. Kind of to English heavy because that's kind of how we saw with Wikipedia. Lastly, the summarization is performed by pointer generator networks. This is a method of performing abstractive summary of text. So there's two types of summarization, abstractive and extractive. And you can think of extractive summarization as being when you take a highlighter and you go over a book and you highlight sentences. And that's what you want to remember. So you're just taking sentences out of the text and putting them into a summary. Contrast that with abstractive summarization. And that's when you take a pen in your book and you just highlight certain phrases. You don't highlight whole words. You just highlight here and there what you think is important. So just thinking about it like that, you can probably see that abstractive summarization is more powerful. It gives you a better summary of your text. Extractive summary, you're probably getting stuff in there that's probably not relevant, and it's not going to be a good summary. But abstractive will give you a summary that makes sense. The problem with abstractive summarization is that it tends to sometimes not be factual because it can pull text from places and put it together and make something that's just not true. Also, it can repeat itself. So if you have a sentence here, it might think this over here is important, and it will start repeating itself. So this paper that came out, I believe it was either earlier this year or late last year, called Pointer Generator Networks, tries to alleviate those two issues. The pointer helps it keep track of the text that's used before, and the generator helps it to not repeat itself. Sakai is the neural machine translation tool being used here. Open source, developed by Amazon on GitHub. It's written in Python 3 and based on MixNet. It's a sequence-to-sequence framework that supports the three big ways of doing neural machine translation today. Deep recurrent neural networks with attention that we heard about this morning, as well as transformer models with self-attention and fully convolutional sequence-to-sequence models. Sakai is something that you can just get from GitHub, and there's really good documentation to start training your own models. And that's exactly the steps I use to do this, nothing fancy. One word of caution is that the translation can take a very long time. On my computer at home, I think I let it go for a week before I said, okay, that's enough, and moved it up to Amazon on one of the P3 instances with GPUs. I let that go for a while, and finally said, okay, that's enough. And then my colleague Suneel gave me a model that they had already made, and it was trained on, I think, 8 P3 instances using multiple GPUs. It still took a long time. So it can take a long time to get a model that gives you good results. For the ones that I did it myself personally, I stopped it early, and the model still worked somewhat. But there is a big difference between my model that I made and models that were allowed to go much longer. So while you certainly can do it, you do need a lot of computing power to make it work. And for this pipeline, we're going to use English to German and German to English, so 2 separate models. And I will... So this is Apache Napa, and this is the flow that implements the pipeline that I just talked about. So if you're not familiar with Napa, it gives you a really fantastic canvas in which you can draw your flow using processors. Each square is a processor that does something to the data going through it. In Napa, the item that flows through the flow is called a flow file. And a flow file has 2 key pieces of information. The first key piece of information is its content. And that can be anything you want it to be. So the content might be the news article it gets back. The content might be a search word. You want the content to stay small because it's kept in memory. But the content can be anything you want. And then flow files have attributes. And attributes are just metadata about the flow file, key value pairs that you can use to help describe your flow file through the process. So we'll walk through this, and I'll show you how it works. So the first processor is called Generate Flow File Processor. All of these processors, except for one at the bottom, come out of the box with Napa. So you're not seeing anything fancy that I did. You can use all of these as they are. So the first one is the generate flow file, and it just starts the flow with a word, and I think the word I picked was automobile. To easy translation between English and German, something simple to start with. But in a real world scenario, you would probably get your search terms from somewhere else, of course. Whether you read it from a file, whether it was a REST endpoint, you can use your imagination on how it might get into your flow. Pretty much anything you can think of will probably be supported. So the flow file that gets generated with the word automobile goes two places. On the top one, it goes to duplicate flow file. And all that does is exactly what it says. It makes a copy of that flow file. And then that copy goes down to translate English to German processor. Now this processor just calls a Python script that's running on this computer. And this Python script calls Sakai, which does the translation and gets the translated term back. Nothing too fancy. The first flow file goes to the extract text processor, and this processor pulls out that search term and puts it into an attribute of the flow file. And the attribute is called search term, to keep things simple so I don't get confused. And then the German translation goes down to update attribute. You can probably guess what it does. It takes that search term and puts it into an attribute on the flow file called search term. So at this point, they now come to the Query Solr processor. They both have an attribute called search term. In one of the flow files, the search term is automobile. In the other flow file, the search term is the German word from automobile, which I should probably learn, but I don't know. So we have both of those. The Query Solr processor reaches out to Solr with that query and says, give me all your stuff with this search term. Nothing fancy happens here. So I've been in talks this morning talking about search ranking and other stuff. You can absolutely still use all of that stuff here. For this example, it doesn't do anything extra fancy. Just executes the search to get the results back. The search results from the Query Solr processor are returned to Napa in XML. So to work with that, there's a processor called split XML that does just that. It splits that XML up into a separate flow file for each of those XML entries, however you want to do it. You give it an XPath and it splits on however you want it to split. So for this one, I split it on each search record. So after the split XML, if we had 10 search results come back, we'll now have 10 flow files, one for each search result. The next processor is called evaluate XPath, and that processor pulls out the file name of the file that was indexed for the search result. Once it gets the evaluate XPath, we now know the file that was indexed that contains it. It goes to the next processor, fetch file. And that fetch file simply reads that file from the file system. So now we have the contents of the search result for each search result. It then goes down to a lang detect processor. This is a custom processor that I wrote. It's up on the GitHub for this presentation. It's very simple. It uses Open NLP's language detection capabilities. Given text, it returns what it thinks that language for that text is. For this one, it will return one of two things. It will return either ENG for English, or it will return DEU for German. The OpenNLP language detection capability can actually detect over 100 languages, but since I know this is either English or German, we know there's only going to be one of those. So you can absolutely extend this to cover multiple languages if you need to. So now that we know the language, the lang detect processor puts the language in an attribute called language. I'm not very creative. Language. And language contains either ENG or DEU. The route on attribute processor determines where in the flow should this go based on this language. If it's German, it comes down to translate German to English. If it's already English, it just keeps going. At this point, we have translated our article. back to English. So by the time we get to this processor, our search results are back in English. And this processor does sentence extract and tokenize. This is a custom processor. The code is also up on my GitHub. It's also a very simple processor as well. It uses Open NLP to pull out each sentence in the article so that the article is now formatted as one sentence per line. That's the required format for the summarization tool. And it tokenizes each of those sentences, so anywhere it needs it. So the output of that is one sentence per line tokenized. And that comes down to the summarized English processor. And this processor just calls a Python command. That's all it does. It executes a Python command on this server to send the text over to the process, to the summarization, to get the summary back. Once it gets it back, it sends it to the log attribute processor, and the log attribute processor simply dumps it to the console, to Napa's log. You could put it anywhere you wanted to here, of course, if you wanted to put it into a database, if you wanted to return it somewhere else, anywhere. Possibilities are really pretty endless there to do whatever you want with it. So that's the Napa flow. Using that, we just made a pipeline, writing a very limited amount of code to do English in, English out searches over multilingual documents. Some links, because each of these technologies are very deep, and you could spend days and days and days. There are good links out there for getting started. The Sakai training tutorial, that's the one I followed. It's very straightforward. It doesn't require any knowledge. It'll pretty much hold your hand through it. It's a great introduction to neural machine translation. The code for the custom Napa processors and the flow that I just showed you, those are on my GitHub. You're free to check them out, see how they work. And lastly, there's a really good page, Attention is All You Need, annotated, and it describes neural networks with attention and how it works. And lastly, thank you. And if you have any questions, I'll be happy to address them. Yes?
The language detector, are you using it for detect the search terms, or are you using it for actual language?
In this one, I only used it for the actual language, but you could do it for the search term as well. In this one, I assumed that the search term would be coming in as English, but if you don't know what language the search term might be coming in as, you absolutely could use the language detection to figure it out and then route it and translate it based on however you need to.
What was that language detector?
Open NLP, Apache Open NLP. Yes?
So in this model, you have to index the both documents, one original and the translated document, right?
No, only the original document. The pipeline,
Actually, okay.
yes, the pipeline does the translation after it returns it.
How is working for, because many documents has a kind of English-German mixed one.
Mm-hmm.
Is it working for mixed one?
I have not tried that. That would be a good thing to try. I have not tried that. Yes?
You said that the Sakai was more expensive than the statistical one. What do you mean by that?
Yes, the training process specifically.
So after the training is done, so for the actual translation of documents.
Much faster.
Okay.
Yes. Yeah, I think it was mentioned in the keynote this morning about how it takes a long time to translate, but then you can execute it and get results very quickly. Yes, it is fast. Yeah. Yes?
What is the latency of the pipeline?
The latency? It is, right now, it's not made, or it's not good for a real-world application right now. This is more of a functional prototype. There's a lot of steps that would need to be done to make it more real-world to be deployed as is. For example, for the translation, when it executes it, it loads the model every time. So things like that could be done better to only load it once and execute it as it goes. Could use some work there. Yes? I did not, no. So in the query processor, You're welcome to do any of that kind of stuff, but for this, no, I did not.
And what's the quality of the summarization? Check that out.
Yes. The best thing is to check out the paper that it came from, the pointer generator a paper. Give you a really good. They said in the paper that it beat the current standard by 2 blue points. So it's just a measure of how summarization, how much it, how well a machine summarized article looks like something that a human would summarize. And it's just a metrics for measuring it. So they say it advances the state of the art. And from what I saw, it works fairly well. There's always cases where things don't make sense. But it's well enough that I could read it and get an idea of what the article was about.
Okay, so that was fairly normal English?
Yes. Yeah. Of course, it did worse when it was a German article translated to English and then summarized. Yes. Yes. Yeah. Any others? Well, thank you very much.